If you look at heavy city traffic through a thermal camera, you'll notice a lot of glowing red wheels. Every time a car slows down, it generates an intense amount of heat. In a traditional gas-powered car, the braking system is purely physical. When you press the pedal, hydraulic calipers force friction pads to aggressively clamp down onto metal rotors attached to the wheels. That mechanical friction acts like a giant eraser for momentum. It takes the forward kinetic energy your engine just worked so hard to create and converts it entirely into raw heat, which simply dissipates into the surrounding air. In stop-and-go city traffic, this century-old design is highly inefficient. Up to 30% of the energy a vehicle consumes is lost simply to the repetitive act of stopping. Electric vehicles approach this problem with a different set of mechanics. They use a system called regenerative braking, which is engineered to capture that momentum and turn it back into usable electricity instead of burning it off. For over 100 years, slowing a car down meant destroying its kinetic energy. Modern electric vehicle design treats deceleration as an opportunity to harvest power. This diagram shows the baseline forward movement of an EV. When you press the accelerator, electricity flows out of the high-voltage battery pack and into the electric motor, which turns the drive shaft and spins the wheels. The moment you lift your foot off the accelerator, that power delivery stops, but the car is still rolling. The momentum of the vehicle pushing those wheels forward now physically forces the electric motor's rotor to keep turning. Without battery power driving it, the spinning electric motor instantly reconfigures into a generator. Inside the motor housing, magnetic forces push back against that turning motion, creating a heavy electromagnetic drag. This internal resistance, or resistive torque, is what actually slows the car down. It applies stopping force directly to the drivetrain, entirely bypassing the need for traditional friction paths. As the generator spins against that magnetic drag, it produces electricity. This raw power is routed through an onboard inverter, converted back into direct current, and fed straight into the main battery pack. The vehicle uses its own rolling mass to refuel itself, creating a closed-loop energy cycle every time the driver eases off the accelerator. Despite this electrical loop, EVs still come equipped with traditional hydraulic friction brakes at all four wheels to handle extreme stops and ensure baseline safety. To manage these two different systems, engineers use a brake-by-wire configuration. This is a software layer that coordinates the electric and mechanical stopping power behind the scenes, without the driver ever feeling the handoff. In daily driving, the division of labor is heavily skewed. Up to 90% in aggressive regeneration modes, the slowing force is so immediate that you can use the accelerator pedal to completely control both your speed and your stopping, rarely needing to touch the brake pedal at all. By capturing roughly 60 to 70% of the car's kinetic energy, this system extends the total driving range of the vehicle by 15 to 20%. You see these gains most clearly in stop-and-go city traffic or on long downhill routes. There is also a distinct mechanical upside. Because the friction pads are rarely used for routine stops, EV brake components often last 2 to 3 times longer than those in standard gas-powered cars. But the system does have physical constraints. In extreme cold weather, cold batteries accept electric charge much slower, meaning the car has to temporarily limit or disable regeneration until the battery warms up. Capacity is another strict limit. If you leave your driveway with a battery charged to exactly 100%, there is zero room to store recovered power. The vehicle automatically relies on friction braking until enough battery capacity opens up. Geographically, the benefits change. On the highway, the system offers almost zero efficiency benefit. While a cruising car has massive kinetic energy, that energy only becomes harvestable when you actually slow down, making regeneration irrelevant during steady-speed travel. Ultimately, this system repositions the act of stopping. Instead of burning off momentum as wasted heat, the vehicle converts deceleration into a purposeful extension of its own range.